Hello everybody, welcome back to the Data Structures and Algorithms Specialization and the Algorithmic Toolbox course within it. This is the last lecture in the introductory unit, and here we're going to give sort of an overview of the course. And in particular, what we're going to do is we're going to talk about sort of the philosophy of the course and how it fits into what we're going to be teaching you within the rest of this course. So there's a problem. Algorithm design is hard, and in particular, it's hard to teach. And by this, I actually mean something pretty specific. Now, algorithms solve many different problems. You can use them to find paths between locations on a map, or find good matchings with some property, or identify images in a photograph. Many different sort of unrelated sounding problems can all be solved by algorithms. And because the sorts of things that an algorithm problem might ask you to do are so varied, there's no unified technique that allows you to solve all of them. And this is different from what you see in a lot of classes. When you're learning linear algebra, they talk about how do you solve systems of linear equations. And they teach you some technique like row reduction, and then you're sort of done. You just sort of need to practice it, and you can solve any system of linear equations. They give you a system of linear equations, you turn the crank on this row reduction technology, and out pops an answer. For algorithms, there isn't that sort of thing. There's no general procedure where I give you an algorithms problem and you sort of plug it into this machine and turn a crank and out pops a good algorithm for it. And this makes it hard to teach. If there was such a thing, we could just teach you, here's this thing that you do this, and you'll have a good algorithm for any problem you might run into. And it's harder than that. I mean, sometimes in order to find a good algorithm, it requires that you have a unique insight. You're working on some problem that no one's ever looked at before. In order to find a good algorithm for it, you need to come up with some clever idea that no one else has ever come up with before. This is why sort of algorithms are so well studied, why there's such an active field of research. There's still so many different new things yet to be discovered there. And I mean, we certainly can't teach you things that haven't been discovered yet. And we also can't teach you things custom tailored to the problems that you are going to run into in your life as a programmer. So since we can't teach you everything you need to know about how to solve all of your algorithms problems, what can we teach you? Well, there are sort of two things. One thing that we can definitely give you is practice designing algorithms. We're going to have lots of homework problems with sort of lots of things for you to work on. And this will give you practice. How do you, given a problem you haven't seen before, come up with a good algorithm for it? Once you have the algorithm, how do you implement it and make sure everything works and runs reasonably well? That's something you can practice. And it turns out that for the type of problems where they're sort of very general and can be many different things, I mean, it's possible to solve a lot of them, and one of the ways to be able to solve them is practice. But we're also going to do more. We're not just going to throw you in the deep end and say, try to swim, try to program all of these algorithms. There is something useful. We can't teach you a generic procedure that will solve any algorithms problem for you. But what we can do is we can give you some common tools, some very useful tools for algorithm design. And especially in this first course in our specialization, we're really going to focus on helping to build up your algorithmic toolbox. And in particular, this course is going to focus on three of the most common and most generally applicable algorithmic design techniques. The first of these is greedy algorithms. This is something where you're trying to construct some big object, and the way you do it is you sort of make one decision in the most greedy, locally optimal way you can. And once you've made that decision, you make another decision in the most greedy, locally optimal way you can. And you just keep making these decisions one at a time until you have an answer. And surprisingly, somehow making these locally optimal decisions gives you a globally optimal solution. And when this happens, it gives you very clean algorithms, and it's great. That's the first thing we'll talk about. Next, we'll talk about divide and conquer, which is a technique where you've got some big problem you're trying to solve. What you do is you break it into a bunch of little pieces, you solve all the pieces, and then you put their answers together to solve the original thing. Finally, we'll talk about dynamic programming. This is a little bit more subtle of a technique. This is what you get when you've got some sort of large problem that has sort of a lot of, not sub-problems, but sort of related problems to it. And this sort of whole family of related problems, their solutions sort of depend on one another in a particular type of way. And when you have this, there's this great trick that you have where you sort of start the small problems at the bottom of the pile and you solve all of them, and you sort of keep track of all of your answers, and you use the answers to the small problems to build up to obtain answers to the larger and larger problems. So these are what we're going to talk about. Each of the techniques, we're going to talk about how do you recognize when it applies, how do you analyze it when it applies, and sort of some practical techniques about sort of how to implement, how to use them, all that good stuff. So there's one other thing before we let you go into the fun world of greedy algorithms that you should keep in mind throughout this course. And that's that there are these maybe different levels of algorithm design. There's sort of different levels of sophistication that go into it. At sort of the very lowest level, or the top of the slide, I guess, there is the naive algorithm. This is sort of a thing where you take the definition of the problem and you turn it into an algorithm. And we saw this for Fibonacci numbers and greatest common divisors. You sort of interpreted the definition of the thing you wanted to compute as an algorithm, and you were done. Now, these things are often very slow, as we saw. Often they look like, in order to find the best way of doing something, we enumerate all ways to do it and then figure out which one's the best. On the other hand, I mean, these are slow, but it's often a good idea to first come up with a naive algorithm. Just make sure you have some algorithm that it works. Sometimes this works well enough and you can just be done with it. Other times it's too slow, but at least you made sure that you understood what problem you were working on and have something that runs. But after that, the next thing that you want to do, if this naive algorithm is too slow, is you try and look at your toolbox. You say, are there any standard techniques that I know that apply here? Maybe there's a greedy algorithm that solves this problem. Or maybe I have to use a dynamic program. But if you can find one of these standard techniques that work, often that doesn't involve too much effort on your part and gives you something that works pretty well. Now, once you have something that works, you often want to optimize it. And there are lots of ways to improve an existing algorithm. Reduce the runtime from n cubed to n squared or n squared to n. And to do this, there are sort of a bunch of things. Maybe sometimes you can sort of rearrange the order in which you do the operations to cut out some of the work that you do. Sometimes you have to introduce a data structure to speed things up. There are a bunch of ways to do this. We'll talk a little bit about how this works. And these three levels are things that you should be comfortable with and able to apply pretty well by the end of this course. However, sometimes these three are not enough. Sometimes the naive algorithm is just too slow, the standard tools don't apply, there's nothing that you can really optimize to improve things. Sometimes in order to get a workable algorithm, what you need is magic. You need some unique insight that no one else has ever had before. You need some sort of clever new idea. And there's only so much we can do to teach you how to produce magic. I mean, we will show you some examples of things that really did have clever ideas that maybe you can't reproduce the thought process that how did you come up with this crazy idea that just happens to make this work? But you should at least be able to appreciate the sort of thought that maybe goes into this sort of thing. In any case, something to keep in mind when looking on it, when thinking about our problems and what sort of things are expected of you. In any case, that is basically it for the introductory segment. We've talked a lot about sort of why algorithms are important and given you some examples. We've talked about asymptotic notation, but now it's time to let you go to the rest of the course. The rest of the course will keep giving you exercises to, hone your skills, and each unit of this course will cover one of these major techniques. After I leave you at the end of the introduction, Michael will pick up and talk to you about greedy algorithms. Next off, Neil will talk to you about divide and conquer. Finally, Pavel will have a unit on dynamic programming. Each of these, they will talk to you about where the technique applies, how to analyze it, how to implement it, all that good stuff. But this is where I leave you. I hope you've enjoyed the introduction, and I will put you in Michael's very capable hands to start learning about greedy algorithms starting in the next lecture. So, until then, farewell.